So welcome again. In this tutorial, I'll be talking about the PGA sub-circuit. Is a programmable gain amplifier sub-circuit. So gain amplifier is used to set program gain using it has an input where you can set the size of gain. This is exactly the input. So through this point, you can actually set what gain should your data have. That is, if you are sending it, probably if you are trying to send it, you can set what gain to program it with. So one thing I have to state is a lot of these sub-circuits are not like the fundamental circuits of a bpsk modem. Like the sub-circuits I've treated already, they are not actually the main fundamental circuits of a bpsk modem. The main sub-circuit is the bpsk modem circuit, which I'll still treat later. So I'm actually treating this sub-circuit because they make up this particular circuit I'm dealing on. But you might meet a different bpsk modem with a different architecture altogether. So just bear in mind, I'm just explaining them because they're actually related to this particular circuit. But the main fundamental part of a bpsk modem, I'm going to treat them later in the sub-circuit also called bpsk modem here. So these are more like the peripherals that make up the surrounding of this whole particular, but you need to understand them to understand the Verilog code that I've written in this my website. Okay, this is this digital signal mode. So I think this is what I'm treating at this. Okay, this is ADC. We've done this also. So this is what. Okay, this is the PSK modem. So on the PGA, programmable gain amplifier, is used to set the gain. How do you want to amplify your signal? So amplifier is out of the scope of this circuit. So but what it basically does is to set this gain here. If you're amplifying the demodulated signal, set what gain will you be using to amplify it. So you set the gain here. The gain is the input you'll be placing. This inter is an interrupt. Then down here, this is the clock. This indicates that yes, you've transmission complete done. Then down here you have your reset. Now this is an Spi output here. Please go back to my previous tutorial to understand how the SPI works, but I'll explain it a little here. I won't explain how they work. But this SPI NCS is the chip select. If it's low, it's transmitting. If it's high, it's off. This is the data that is being transmitted. It comes out here, and this is the SPI clock here. So is for this circuit. This particular first part of this circuit is the clock frequency divider. Just like I told you, the frequency divider makes up is a fundamental circuit you have to learn when you are dealing with Verilog. Because in practical sense, most of the time you might have multiple sub-circuits that are being operated at different frequencies. So you have to be able to generate these sub-frequencies from the main clock frequency of the circuit. So this circuit here is still the same with the one we met in the last tutorial. So it's a fundamental circuit of every FPGA design. So I've circled it. That's what it basically does. So after the generation, it comes out here. So that clock is the clock that will be used for this SPI down here. For the SPI clock, that's what we generated up here. Is almost the same with the TS clock. The transmit clock is 4 megahertz for this particular circuit, and the SPI clock is 2 megahertz. But this is how we generated it. Remember I told you earlier that we have 200 megahertz of clock in 200 megahertz from the initial circuit. The main clock frequency of this whole circuit is assumed to be 200 megahertz. So if you are trying to generate 4 megahertz from it, then you are going to do 200 megahertz divided by 50, and 50 in hexadecimal is 32. So this is the 32 here. So this is it. In decimal is 50, in hexadecimal is 32. So that is how we got this our counter value 32. This is the normal adder and this is the reset. So if you understand my frequency divider circuit, this won't be a problem for you. This 32 here represents 50. That is, if you divide our 200 megahertz clock frequency, you get 4 megahertz. So that 4 megahertz is the transmit clock. Then half of it, you see how we divided it into 2. Somewhere around here, it was divided into 2 to give us the SPI clock. So when I get to this part, I will explain it also. But for now, that is how we generated it. So now you can see that, let me highlight them. This is the central reset. I've highlighted it. You can see how it went into all the resets of this sub-circuit. Now this is the main clock, the 200 megahertz clock frequency. You can see how and where it went to. And then you now see our generated clock here, the 4 megahertz. Come down and you see where it entered. So I will explain why they were at these particular places. So, but just note that this particular sub-circuit generated is used to generate the 4 megahertz. When you go through the code, you will see it also. Now, this int bit is our interrupt enable bit. Is used to send an interrupt signal. So whenever it comes on, it means that an interrupt, a transmit interrupt has been sent. That is more like a start button for the transmission to transmit this gain. So whenever you are done setting the value of this gain, whenever you set this value of this gain, you set this interrupt enable bit here. So once the interrupt enable bit is sent, the transmission starts. So what actually happens here is this. Now see this our AND sub-circuit here. So the reason we have this AND sub-circuit instead of just having the interrupt is because of double triggering. So we want this interrupt to occur like a pause instead of staying on continuously. You know, if you turn it on, if you turn this interrupt on, it stays on for a long time. But with this, we can generate a pause from it. That is to say, now see, it's used to trigger it for one time triggering. So the interrupt comes here and checks if the interrupt has been enabled and there have not been an interrupt before. Look closely and understand. This D flip-flop here stores the initial state. So what it's trying to say here is that if initially is not on and then you turn it on now, it should come on. I know whenever it comes on, it likewise goes here and then comes down here again, and whenever it comes here, this will now be off and this is going to be off. So it's used for one single pulse triggering. Let me explain it another time again. So this, whenever you turn this interrupt on, it comes here and goes through here. So at this AND gate here, what it checks for is if the interrupt is on one and here is off. Here represents the initial state because it's going to pass through this flip-flop and then come out on the next clock cycle. So if it says if it's not on initially, now turn it on. So, and whenever you now turn it on the next clock cycle, that on will also pass through here. And whenever it gets here, if it's on here, that means it's off. So it's going to turn this particular place off. So it's used for single pulse triggering of the interrupt. So you now find out that the interrupt is going to trigger one time. So that's it. Then again, this is the RAM. This particular setup is for storing this gain that we would like to transmit. I'm sorry I was interrupted for a while now. So the gain, which is the major reason for this circuit, this is where once you give the gain of the amplifier, it goes in through here. Sorry, it is a splitter. Here is just 0 0. All these places are not needed. This is the main gain that comes in here, and it's only going to set when this is on. When this, let me highlight this. You can see I've highlighted this, which is what turns this multiplexer on, and it's coming from this interrupt. So whenever the interrupt is set, and you know the interrupt comes as a pulse, remember that's the essence of this AND gate. So it comes as a pulse. So whenever it comes, it's going to pulse, set a pulse on this multiplexer. It's going to give a 1 for 1 clock cycle. Whenever it gives that one, the gain is latched within this RAM here. So you can see this is RAM 16 bits of RAM. It means 16 flip-flops together. So that is how the gain, which we are trying to, the gain of the amplifier, is programmable. So that's how we set it here using this multiplexer and this RAM. The RAM latches it. We are going to see how we use it. So let's talk about this 4 bits TX enable, done bit, TX done, and TX done prev. TX done prev means TX done previous. The previous means whenever this TX done comes on, the next clock cycle it goes here. So that's why they call it TX done prev. Alright, let me see. Yes, that's it. So that's why they call it. It takes the TX done, the previous, which is now this one, and now brings it down here. So they are basically the same bits, but in different clock cycles. So it first of all comes here, then next clock cycle it goes here. So now let's watch and see how these 4 bits are being set. Now whenever this interrupt is set, you can see the multiplexers that comes on. 3 multiplexers are going to come on. 1, 2, and 3. Right? I don't know, I've messed up this video. I don't know where exactly I stopped. Oh god, I've messed it up actually. Let me start from this TX enabled again. I don't know. So this is the gain. The gain actually is what you want to transmit here. This is it here. So this is the RAM that stores it. So it goes in through here and pass through this multiplexer here, and it gets latched within this RAM 16. It turns on with this. This is what turns it on here, and is the interrupt in our interrupt bit. And remember, the interrupt is just a single pulse. So whenever it pulses, it latches the gain in this RAM 16 here. So that's how the gain is latched. We are going to see what it's used for and how it's being transmitted using SPI later. So then let's talk about this TS enabled bit and also this done bit. So at the end of the transmission, the TS done comes on. I highlighted here, this is the TS done. Whenever it comes on and this TS done previous is not on, our done bit comes on. and on the next clock cycle, whenever it's on, it sets it back to 0 here. So that's how this done bit works. Now this TS enabled is a bit opposite to it, and this is it. Whenever the interrupt is enabled, the TS enabled comes on. That is marks the beginning of a transmission. Then what is now these are opposite. You can watch this AND gate, this AND gate here, and this AND gate here. So they are copy opposites. So it's a different thing here. It says whenever, so for this one it says whenever the TS done previous, is it here, is on, and the TS done here is off, it should set the TS enabled to 0, and that is how the TS enabled is being reset. So a lot these are just signals for turning on and turning off it here. Now another major part here is this TX index. The TX index is just a counter. You can see a lot of places where it's affected using comparator. So the comparators were used to check what value is it counting at. So take for instance, let's see how the TX index is being set up. So the TX index is just around there. Now let's see here. So whenever this multiplexer comes on, it sets the TS index to 0. What does it mean? It resets it. So and what is it? It checks if the TS index is equal to 22. 22 in hexadecimal, in binary 22, see 22 in hexadecimal, in binary is 34. So normally is a 32-bit transmission, some stuff, but here it checks, let's see, it checks whenever it counts up to 34 here is equal to 34, it should reset this TS index here. Now this one checks if it's less than 34. This is it here. If it's less than, here it checks if it's equal to. So if it's less than 34, it should do this. It should increment the TS index. So here, this one is just to enable it. So here works with the TX enabled. Is it here? Let me go up. So you can see is the TX enabled that enables this TX index. So whenever the TX index comes on, it enables this TX enable comes on, it enables the TX index, and that is how it counts. If it's less than 34, increment it. If it's greater than 34, reset it to 0. So it's actually a 0 to 34 bit counter. That's what it is. It counts only to 34 and starts afresh. Now for the SPI, let me briefly talk about this TS bit. This TS bit, the input here is a TS bit, which is this, which is our gain bit that we want to transmit. So that's why I call it TS bit. That the gain we want to transmit, we want to set the gain. So that's where it goes into this TS bit. And another thing that goes into this subcircuit again is the TX index, which is this our counter here. Then it has an output, and that output is what actually goes out to this SPI output, the transmission we want to do. So let me show you this TS bit, what it does. This is it here. Remember the two inputs here are the TS bit and the TX index. So here is just a shifter. I shift by 1. Remember, I shift by 1 in actual sense means divide by 2. Is a division by 2. Whenever you see I shift by 1, if you are shifting by 2, it means divide by 4. If you are shift by 3, it means divide by 8. If you are doing the opposite way, if you are left shift by 1, it means multiply by 2. So that is it. So remember our TS index counts up to 32. So that means whatever is counting is being divided by 2. So assuming the value of this TS index is 32, that means the output here is 16. If the value of TS index is 4, the output here is 2. If the value of index here is 11, okay, now for odd numbers, if it's the 11, it's still 5 because here it's counting in bits. So there's no the decimal part and there's no approximation. So 11 and 10 are the same thing. 6 and 7 are the same thing. So half of 6 is 3. Half of 7 is 3.5. So the half is gone. So 6 and 7 are 3, the same thing, 3 or 3. So that's how this TS index is being divided. Then, reason why we use this thing is because the TS bit which we want to send is 16. See, is a 16-bit value, whereas our TS index is 32. It counts up to 32 and we want to transmit 16-bit stuff. So that's why we always divide the value so that it is going to be from 1 to 16 instead of from 1 to 32. It divides it until it gets to 1 to 16. So therefore, if there is 1 here, we have 1 here. So it's talking about, so whatever the TS index is what we are going to get at the output. So assuming the TS bit is 1, assuming the TS bit is 2, then it's going to pass through here. Assuming it's 10, it passes through here. We are going to have 5 at the output. So if 5 goes here, it's going to take the fifth 1, 2, 3, 4, 5, which is the fourth one, which is going to be 1, 2, 3, 4, 5. This 0 here. Then assuming the value of TS index is 18, it passes through here. You are going to get 9 at the output here. So you check the 9th bit should be this 0 here. So that is why they divided it by 2 here. And they take only, okay, not here yet. So that is why, remember I told you that our main clock is 200 megahertz, the transmit bit is 4 megahertz, and the SPI clock is 2 megahertz. So this is why the division was done, because it's going to take only a particular, either takes the even part or the odd part. That is because the odd and the even gives the same value. 6 and 7 will give the same value. 10 and 11 will give the same value. 19 and 18 will give the same value. So if the TS index is counting 1, 2, 3, 4, so it's almost like it's counting 2, 4, 6, 8, 10, 12, 14, because the other odd numbers are yielding the same value. So that is why we actually divided the transmit clock again by 2 to get 2 megahertz, because one of the counting numbers are being skipped, the odd numbers. So that is why you now get this output. So this circuit is actually used to convert this TS bit from parallel to serial. Is a more of a parallel to serial outputting. So we are putting 0, 1, 2, 3, 4, depending on the value of the TX index. So that is what this sub-circuit does. So let's go back and see how it fits into this PGA. You can see where it entered. So the TS bit, TS index giving you that output. So that output is what is going to go through as the SPI output. So that is the output of our SPI. The output you want to send is a 16-bit, and that 16-bit is this one. Is this one here, because it contains our gain. We can trace it by highlighting this. By highlighting this, that we'll see where it ended up to. So you can see it went into our sub-circuit and came out serially through this out, and goes in through here, and then goes out through the SPI output. And then again, you can watch this also. Let me zoom it in. Sorry, I'll zoom out very soon. Watch here. So this is why the division of the clock happened, dividing 4 megahertz to get 2 megahertz. Because if you are using 4 megahertz, it means that you are transmitting every clock cycle. But because you were dividing, remember I told you about the odd and the even number giving the same output. So they are now taking only either the positive or the negative. So now they are asking, so once you take this first bit, that is the last bit of the TX index. Let me highlight it so you see. We're on the TX index here. The last bit from it is enough to tell you whether it's if it ends with a 0, it means it's an even number. For every binary number, it's still the same thing. If it ends with a 0, if a binary number ends with a 0, it's an even number. If it ends with a 1, it's an odd number. So this 0 here, it checks if the 0 bit of, that is the LSB of the TX index. If it's a 1, that is if it's an odd number, set it to 1. That is what it does. So it only sets the SPI clock to 1 whenever there is an odd number. Then once it's an even number, it sets it to 0. So that is how this SPI is being clocked. So whenever the last bit of the TX index is a odd number, is 1. If it's an even number, is 0. And you know odd and even number interchange immediately. So this SPI clock actually clocks on and off and on and off. That is making it half of the 4 megahertz TX clock. So that is this about this tutorial. You can ask your questions. Then let's see where it actually fits in into the general circuit. So let's see here. Oh, sorry, I've actually fixed it. So this is how it all happens here. This is the SPI output, the usual clock and reset. Then this is the gain input here, the gain we want to add. Then this int here, I'll show you later. The interrupt, the int means the interrupt. This is where it comes from. So when I'll be talking about this PLC, I'll show you the int. You're going to see it in many parts of this tutorial. So that is it for this. Thank you and subscribe to my channel.